Hello, welcome to Advanced Composites. Today is the start of the last week of this course, that is the 12th week of this particular course, and what we plan to do over the span of this course is finish our discussion on buckling, which we have had specifically in the last week, and then in the remaining part of the week we will introduce a new topic related to short fiber composites, because these types of composites are very widely used in the industry, and we will discuss how to analyze these types of composites also. So, the first part we will discuss a little bit more about buckling phenomena, and then we will move into the area of short fiber composites, and with this we will have a closure to this particular course on advanced composites. So, earlier we have discussed buckling of composite plates when they are subjected to compressive loads, and the direction of the compressive loads is normal to the plane of the to the edge. So, if this is the edge, then the compressive force is normal to this edge, it may also be normal to the other edge. Today we are going to discuss a slightly different type of buckling known as shear buckling. So, and in this the plate is subjected to in plane shear loads, and because of those shear loads also the plate may buckle if the shear loads exceed a particular threshold. So, this is a type of buckling which we will like to understand better, especially in context of composite plates, and let us see how we analyze these types of problems. So, our theme is shear buckling. So, to give you an idea how shear buckling works is, suppose this is a composite plate. So, if I subject it to normal loads, it buckles like this, or if I subject it to the normal load in this direction, then it will buckle like this. But it may also buckle in shear, because if I subject it to shear forces, so then it tends to do this thing. Okay. So, in this case the deflection pattern is something like this, but when it buckles in shear, then its deflection pattern is a little more complicated. So, this is the type of buckling we will like to discuss. So, schematically, if I have a rectangular composite plate, and I will be subjecting it to shear . And so, this is being subjected to shear stresses or shear forces on all of its edges. Okay. Now, of course, if I subject a plate to a shear, it will also tend to rotate. So, I do not want that the plate should rotate, otherwise it will be free to rotate and it will just. So, the way what I do is that I pin these points, okay, corners of the plate. So, what are my boundary conditions? So, for specifying boundary conditions, first I need to know what is the coordinate system. So, my coordinate system is, this is my x axis and this is the y axis. Okay. So, at x is equal to 0. So, this is the corner, x is equal to 0, and at x is equal to a, w is equal to 0 and mx is equal to 0, which means that the plate is simply supported on these two edges. And similarly, I am also going to simply support the plate on the other two edges as well. So, if that is the case, then on y is equal to 0 and y is equal to b. So, what is A? A is the length of the plate and b is the width of the plate. So, on the other two edges also the out of plane deflection W naught is 0 and My is 0 because it is simply supported. But the other extra condition I am going to specify, so that buckling actually happens, is that I am going to pin these points. So, let us call this point 1 and let us call this point 2. So, at points 1 and at point 2, u is equal to v is equal to w is equal to 0. So, these are all mid plane displacements, and this is what the boundary conditions look like. And what is the shear force which is being applied? So, let us call that, so I am applying a shear force resultant and it is S on all four sides. Okay. So, it is S newtons per meter. So, that is the shear force resultant. Now, so the question is, at what value of S will the plate buckle? So, once again, to solve this problem, we have to solve the differential equation associated with the z direction, and before we do that, we assume that the plate is symmetric. So, lamination is symmetric, and if it is symmetric, then I can say that the B matrix is a null matrix. The other thing is that the plate is especially orthotropic. And if that is the case, then I can say that A16 is equal to A26 is equal to D16 is equal to D26, and this is all 0. So, because of these reasons, because of symmetry, the out of plane equilibrium equation and the in plane equilibrium equations, they are decoupled. So, because B is 0, out of plane equilibrium equation is decoupled with in plane equilibrium equation. Okay. So, what that means is that I can now use this only the third equation, and if I solve the third equation, then I should be able to predict at what value of S will the system buckle. So, the partial differential equation which I am going to address is minus Nx del 2 W over del x square minus Ny del 2 W over del y square minus Nxy del 2 W over del x del y plus D11 del 4 W over del x square plus 2 D12 plus 2 D66 del 4 W over del x square del y square plus D22 del 4 W over del y 4. Yeah. So, this del should be del x 4, and all this should equal q of x y. Now, in our equation, q is equal to 0, and because the plate is nice rectangular symmetric lamination, then because of the geometry and all that, nx inside the plate is also 0, ny is also 0, and nxy is same as s, because the plate is nice rectangular and it is uniformly loaded on the external edges by uniformly applied nxy whose value is s. So, at every point we will assume that it is the same thing. So, if that is the case, then my simplified PDE becomes minus s del 2 w over del x del y plus d11 del 4 w over del x4 plus 2 d12 plus 2 d66 del 4 w over del x square del y square plus d22 del 4 w over del y4 equals 0. So, this is the differential equation I want to solve, and I have to also meet all the boundary conditions, and if I can do that, then for some value of s I can calculate when the value of w will become a real number. So, we have to solve this equation, and the way we are going to solve it is that we are going to use special Galerkin method. Special Galerkin method. So, if that is the case, then what is the first step? The first step is that we have to choose a displacement function for w. So, we have to guess a displacement function for w which meets all the kinematic boundary conditions. So, select appropriate w. So, once again these are all mid plane displacements. So, we assume that w naught x y is a series and this is a m n sin m pi x over a sin n pi y over b. Okay. And this is being integrated from 1 to m capital M and 1 to capital N. So, this w x y, it is equal to 0 on all the 4 edges. So, it is 0 at x is equal to 0 edge, x is equal to a edge, y is equal to 0 edge and y is equal to b edge. So, what does that mean? All kinematic BCs satisfied. So, this is number 1. So, once we have selected such a function, then what is the next step? We have to calculate the residue. We have to plug this back into the equation, find out the residue and integrate that residue, its weighted integral over the domain of the plate. So, the second step is I integrate this thing from 0 to a, 0 to b, the residue, and I just do not integrate the residue, I integrate it after applying some appropriate weight function. And I am integrating it over the domain and I set it to 0. Now, in special Galerkin method, this weight function is what? It is same as assumed displacement function. Okay. What will this be? So, it will be, so what is our assumed displacement function? It is sin m pi x over a times sin n pi y over b. So, this is same as sin m pi x over a times sin n pi y over b. So, we actually plug this in and it will be times w m n 1, okay, some constant. So, what I do is I plug it all this in. So, what is the residue? First we will develop an expression for residue. So, my residue is minus s times the second derivative of w with respect to x and y. So, it is m n pi square over a b cosine pi x m over a cosine pi y over b plus, and of course I have to multiply it by a m n. So, I will take the a m n outside the bracket, that is not a problem. Okay. And then I get all these terms related to d's. So, d 11 m pi over a to the power of 4 plus 2 d 12 plus 2 d 66 m n pi square over a b, the whole thing squared, plus d 22 n pi over b, whole thing to the power of 4, and this entire thing in parenthesis curly brackets, this is being multiplied by sine pi x m over a sine pi y n over b, and I forgot an n here. So, I am going to put it back there, and this entire thing is multiplied by a m n, and it is being added up, summed from 0 to m, capital M, and 0 to or 1 to capital N. So, this is my residue. So, this is this long expression of residue I put it here, and weight function also I put m pi x, m pi y. So, one thing I will make a distinction, that here I will not put indices m and n, but rather I will put I and j, and then I will just iterate. So, if I okay, so total number of unknowns. So, if I have to, so what is the unknown, what is it that we are trying to calculate? We are trying to calculate, we are trying to calculate w naught x y. We already know these functions. The thing which we do not know is a m n. Okay. So, if m and n, these are the values, then total unknowns, total number of unknowns is what? M times n. Okay. So, what we are interested in finding out is m times n unknowns, which are a m n. Okay. So, a 11, a 12 and so on and so forth till a capital M and a capital N. So, what do I do? The way we do it is that from this we have to generate m times n equations. Okay. So, the way we generate it is that first I multiply the residue by sine pi x over a. So, I set the value of I and j as 1, I get one equation. Then in the second equation I put I is equal to 1 and j is equal to 2, and like this I keep on increasing j till it becomes capital N. Then I change the value of I to 2, and then I again. So, these are trial functions or weight functions, and we can generate these m times n equations by selecting different values of I and j, and I can change this index I from 1 to capital M and j from 1 to capital N, and in that way I can generate m times n equations. Okay. If I do all the math, finally what we get is, this is the equation we get in a general way, pi to the power of 4 times d11 m to the power of 4 plus 2 d12 plus 2 d66 m square n square r square plus d22 n4 r4 amn minus 32 mn r cube b square s summation of mij aij equals 0. Okay. So, this is a long equation, and this is not just one equation. So, here I goes from 1 to m and j goes from 1 to n. So, this single relation, it represents actually m times n relations, it is not one equation. Okay. So, these are different m times n equations, and there is a typo here. So, here it should be r to the power of 4. Okay. And what is r? R is the aspect ratio A over B, and then you will say what is S? S we already know, it is the external shear resultant, and then what is Mij? So, Mij, if we do the integral, it is equal to I times j divided by m square minus I square times n square minus j square. So, this is the value of Mij if m plus or minus I is odd and n plus minus j is odd. So, both of the conditions, m plus minus I should be odd and also n plus minus j should also be odd. If that is not the case, then, so this is the case, else, so if either one of these m plus minus I or n plus minus j is even, then this Mij is equal to 0. Okay. So, in this way we get m plus n equations, and then we solve for these equations. Okay. We solve for these equations. So, this is what we will actually discuss further tomorrow. So, what we have done till so far is that using the equilibrium equation for the third direction, we have developed this longish expression, and this one single expression represents m times n equations, and using this m times n equations we can calculate the critical value of S at which the plate will start to buckle. And how is it that we are going to calculate? That is something we will see in tomorrow's lecture. Thank you, and I look forward to seeing you tomorrow.